All right, so now we're going to discuss nuclear chemistry. So nuclear chemistry is quite different from a lot of the other chemistries that we've covered in this class. Most chemical reactions that we discuss, actually everything we've discussed up until this point, have been about making and breaking chemical bonds. And chemical bonds are made of electrons, right? When we talk about a covalent bond, that's electrons that are being shared. So if we rearrange, or so if we take a covalent compound and we do, let's say, a combustion reaction, what we're really doing is reorganizing what atoms are bound to what. And so we're really just changing around electrons, right? Nuclear chemistry is chemistry that occurs within the nucleus of an atom. Okay, so now we're not talking about the electrons. We're not talking about bonds between atoms. We're specifically focusing in on one particular atom and the chemistry that occurs within that particular nucleus. Okay, so just kind of to give you a preview here, what we're going to see is we're going to have like the nucleus of an atom. And what's going to happen is a series of nuclear chemistry reactions where then the nucleus of this atom changes. So for example, it might break apart into two smaller pieces, right? But again, we're not rearranging bonds. We're taking one atom and it's breaking apart into two smaller atoms. All right, so first of all, we don't really spend much time talking about the nucleus of an atom because it just kind of exists there. There's nothing really special about it other than it's holding those electrons in place. And again, a lot of chemical reactions that we're interested in are focused on electrons, valence electrons, all that jazz. So, but zooming in now, focusing on that nucleus, right? The nucleus is composed of two what are called nucleons. The neutron and the proton. So this word nucleon is probably a new word. This is the class of particle. All right, so now sort of thinking in terms of like more like upper level physics, kind of particle physics. It turns out that the physicists have found that all the particles in this universe fall into a few different bins. The bin that contains protons and neutrons are what are called nucleons. Okay, we know that neutrons have a zero charge, they're neutral, whereas protons have a charge of +1. Okay, but they're sort of all composed of the same fundamental particles, what are called, quarks. Okay, so they all sort of fall into this class of nucleons. All right, and one of the things that I think is naturally kind of confusing about the nucleus of an atom is this idea of like, well, we know that opposites attract, so positive charges and negative charges are attracted to one another. That makes sense. But within the nucleus, you just have a bunch of protons, which are positively charged, and a bunch of neutrons, which are neutral. And protons are supposed to repel one another, right? Because they don't have opposite charges, they have like charges. Like charges repel. So how the heck do you pack all these things into this like super dense center of an atom? Why is this thing being held together? So nucleons have this very special interaction that goes beyond charge-charge interaction, something that physicists have called the strong force. I know they got super creative with that one, huh? But this is just a special name for this attractive force that occurs between nucleons. All right, so it turns out that all nucleons, just by virtue of being a part of this special class nucleon, have this what's called strong force, which is this attractive force that holds things together. Okay, so only matters across very short distances. But that's how you're able to pack protons and neutrons together into this very dense nuclei of an atom, because they have, once you get them close enough, that repulsive force from the charge-charge interaction is being dominated by instead an attractive force, this what we call the strong force. Okay, so that's why if you take two atoms that are very far apart and try to smush them together, two nuclei, two protons, for example, try to bring them together, they're going to be very repulsive until you get them really, really close. And then all of a sudden, this strong force takes over. And that's why a nucleus exists with with protons and neutrons, right? So this weird new force that we've never talked about before, what physicists call the strong force, occurs only between nucleons, which are what neutrons and protons are. And that's the force that's holding together that nucleus, right? That's why protons and neutrons come together and form the nucleus of an atom to begin with. Okay, so it turns out that not all combinations of protons and neutrons is necessarily favorable. Okay, if we look at this chart here, what we see in yellow, let me do this actually. These are all the possible nuclei of an atom, what are called nucleides sometimes. I guess just to be clear, we'll do a new vocab word here. So a nucleide is a nucleus of a specific isotope. So for example, if I said carbon 13, this would be considered, right? So this is just to pick apart these symbols. This number up top is what's called the mass number. And the mass number is the number of protons plus the number of neutrons. And down at the bottom here, you just have the atomic number, the number of protons. All right, this symbol right here would represent what we would call the carbon 13 isotope. Right, so when we're naming a specific isotope, we're talking about, we do the name of the element dash mass number, right? And let's just remember what an isotope is. These are atoms with the same number of protons, but a different number of neutrons. Right, so that would be one particular isotope of carbon. It's not the most stable one, though. The most stable isotope of carbon is carbon 12. Right, if I had a carbon 13 atom in one hand, it would have 6 protons and 7 neutrons, which is how I got the mass number of 13. If I had a carbon 12 atom in another hand, it would have 6 protons and 6 neutrons. Both of them have 6 protons because that's what makes carbon carbon, right? But they can have a different number of neutrons and still be that same element. And we would call those different isotopes of that same element. Okay, so then the particular combination in the nucleus of, for example, 6 protons and 6 neutrons is what we would call a particular nuclide. I honestly use the word nuclei more to just generally refer to the nucleus of an atom, but the book especially uses this particular term. So just to throw it out there, make sure that we all know what we're talking about here. Okay, so again, back to this graph here. So first of all, let's pick apart the axes of this graph before we dive into what's being plotted here. So on the bottom is just the atomic number, which is of course equal to the number of protons in a particular element, right? When you look on your periodic table and you see carbon listed under element 6, that's because it has 6 protons. That's what makes a carbon atom a carbon atom. And then on the y-axis, what's being plotted is the number of neutrons. Okay. So we can see, first of all, that our very small elements, well, actually, let's pick apart what these dots mean first. So in green here, where am I going to put this? We have all the stable nucleides, right? So for example, carbon 6 is listed in green here. Carbon 12 is listed in green here because that's a stable isotope of carbon. And then everything in yellow is all the unstable nucleides that exist. Nucleides. Okay. So if we sort of zoom in here, we said that this dot represented carbon 12 with 6 protons and 6 neutrons. Well, it turns out that you could also have a carbon atom, same number of, I guess it would be right above it, same number of protons, but now having more neutrons, I don't know, 9 neutrons, something like that. And that thing would not be stable, right? So it might not, so you might be able to form it in a lab really quickly, but it wouldn't be stable. It would quickly fall apart, right? Or otherwise undergo a nuclear reaction until it reached a stable nuclei. All right, so first of all, what this chart is saying is that there are way more unstable nucleides out there than there are stable ones, right? So most atoms have only a very small amount of stable isotopes. And if you had anything else, it wouldn't be stable. It would quickly react, quickly fall apart. All right. The other thing that we can note is that on this line here, this red line, this would sort of represent atoms that had the same number of protons as they did neutrons. And we can see that at the very beginning of the periodic table, the smaller elements, they pretty much have the same number of protons and neutrons. That's like a normal thing. But as they get bigger and bigger and bigger, there has to be more neutrons than there are protons in order for that nuclide to be stable. Right? So since it's above this red line here, that means that that atom has more neutrons than it does protons. And we can see that there's this general trend, right? Other than at the very beginning here, you need to increase the number of neutrons you have relative to the number of protons in order for that thing to actually be stable. All right. And then the last thing we want to note about this graph is there's like this hard cutoff, right? All of a sudden, after a particular atomic number, and that atomic number is 82. Wait, I think I lied. 83. Those atoms are no longer stable, right? So those larger elements, regardless of the combination of protons and neutrons, they're just not stable. They will eventually fall apart. Right? So this is what we would consider to be our radioactive elements, those ones like uranium and plutonium. We've kind of harvested them for creating nuclear power. That's because when you find a uranium atom, you know for sure it's not going to stay a uranium atom for very long. It's going to eventually undergo some sort of a nuclear reaction, which we haven't talked about yet. That's what we're about to talk about here. But it would be unstable, right? So it would react until it formed one of these more stable isotopes here. All right. So we're gonna revisit this chart in a minute here, but now we're going to talk about these different types of nuclear reactions. Okay. So the first thing we need to do is, first skill that we need, don't you freeze on me. Okay, cool. All right, so the first skill that we need is to just know how to balance these nuclear chemical equations. All right, so for example, we said that uranium, because it's a larger element, it's got 92 protons, right? So it's above that 83 cutoff. It's not going to be stable. And in particular, the isotope of uranium that's sort of harvested because it's the most powerful is 238, okay? And so what's going to happen is if you have a uranium-238 atom, it's eventually going to decompose into two smaller pieces, or decay into two smaller pieces, one of which is a helium atom. Okay. And what else? All right. And so this is going to be your first sort of challenge of this particular chapter, is to balance these equations. And it's actually super straightforward here. Balancing nuclear equations just operates on one simple principle, and that is this idea of conservation of mass. Meaning that the number of protons on the left has to equal the number of protons on the right. And the number protons, we do with the little p with the plus sign, and the number of neutrons on the left has to equal the number of neutrons on the right. Okay, so with that in mind, take a second and see if you can't figure out what should go here. We're going to do that as our first iClicker problem. When you get the atomic symbol, the symbol of that element, you can put that in as your first iClicker problem here. All right, I got 92 protons on the left, right? That's my atomic symbol for uranium here. That's what that 92 means. It means that uranium has 92 protons. That's what makes it uranium. And I have to have the same number on the right-hand side as well, right? Because I have to have that conservation of mass. Protons aren't going to be like created or destroyed out of nothing, right? So then what's going to go here? Well, two of those protons made their way into this helium atom, right? Which means that the other 90 are going to belong to the other chunk that this thing degraded into, right? It broke up into these two pieces. One of them has those 2 protons, so the other chunk has to have 90 protons. That would make it thorium, TH. And here's some weird elements you've never heard of before working with nuclear chemistry. And likewise, there has to be this conservation of mass principle that applies to the mass number as well. So if my mass number on the left-hand side is that 238, it's going to decompose into this mass number here. And that means all the other mass is going to wind up in my thorium. So this would be 234, right? Because the amount on the left-hand side equals the amount on the right-hand side, right? 4 plus 234 gives me my 238. All right, so that's how we balance a nuclear equation here. Let's just do another one for the sake of practice. All right, so again, take a second and tell me what my next element is going to be here. When you get that element symbol, you can put it in as your iClicker answer. All right, cool. So I think everybody gets the name of the game here, right? So 35 phosphorus because I have 15 protons, so element 15. My mass number is 35 because 35 plus 4 is how I get my 39, right? So same on the left as it is on the right. It's that straightforward. All right, so got balancing down, not too bad. Make some room here. Now we're going to talk about the types of nuclear chemical, how do we say this? Types of nuclear reactions. It turns out that if looking at nuclear chemistry, you see the same sort of 5 patterns over and over and over again. There are certain modes in which these nuclear reactions will occur. And so we're going to talk about those categories now. The first one is what's called alpha decay. All right. And that is exactly what we just looked at up here. This was an example of an alpha decay. I'm going to just rearrange this equation. Doesn't matter too much, but just to space things out. Okay. This is a specific mode of nuclear reactions, nuclear decay, specifically happening for very large elements. And we'll talk about sort of how we can look at a periodic table and figure out where it's, what type of mode it's going to be. But just FYI, this occurs for very large elements. And the key here is this helium atom that's being displaced here. Okay, so helium 4, right, would be the specific isotope. This is what we call an alpha particle. All right, so any time you have a very large nuclei and it splits up into helium and then one thing smaller, always going to be 2 less, that's what we call alpha decay. Okay, the one on the left we call the parent nuclide, and then the one on the right, the other big one, we call the daughter nuclide. All right, and then again, that helium that's being shot out is that alpha particle. All right, so we got alpha. The next one is what's called beta decay. And in beta decay, you see something that's pretty cool, which is that a neutron, it isn't quite simply the split that you saw in alpha decay. What happens in a beta decay is that a neutron in that nuclei is actually going to convert itself into a proton and an electron. that electron gets ejected, and that's what we call the beta particle. All right. So in a beta decay, you have this nucleus, right? One of the neutrons is not happy, and it's going to then switch and become a proton and an electron, and that electron ends up getting lost. So what this would look like here is if we had a particular isotope like carbon-14, if this underwent beta decay, what that's going to look like is one of those neutrons is going to become a proton. So my mass number stays the same because my total of protons plus neutrons stays the same. But again, one of those neutrons has become a proton. So I'm going to increase my atomic number by 1, increase the number of protons by 1. All right, so a carbon-14 atom becomes a nitrogen-14 atom, and again, an electron gets ejected. So this is how we do electrons in nuclear chemistry. So this is the symbol for an electron. Again, we call that a beta particle in this particular reaction. And notice that our conservation principle still holds, right? If we summed up all the mass numbers, we would get the same value. And if we summed up all of these here, we would also get the same value on the left and the right, right? So nuclear equations are specifically written in such a way where these things are balanced. Importantly, the one thing I want to sort of just stress here is that beta decay is not any time an atom loses an electron, right? Like a sodium atom will lose an electron to become a sodium ion. It's specifically when the neutron becomes a proton and an electron, and that electron gets ejected, right? So that's kind of the key. Even though in the symbol here we have this electron, the real key here is that a neutron is being converted into a proton and an electron. Okay, and we can see that as a consequence to this particular setup here, the number of protons increases, goes up by 1. All right, so beta decay, you're actually increasing your atomic number. All right. The next one, let's actually go to a new sheet here. Is going down the Greek alphabet here, what we call gamma decay, actually gamma ray emission. Okay. So first of all, what's being emitted here is what's called a gamma ray, which is just a very high energy photon. Right? Remember, photons are particles that make up electromagnetic radiation. So light is made up of photons. That's what's kind of being streamed down at you from your light bulb overhead right now, is a stream of photons. But we can only see within this very narrow region of that electromagnetic spectrum. There are waves that are longer than that and shorter than that. The highest energy of those photons are what are called gamma rays. Okay, even higher energy than X-rays. Okay, so a gamma ray is a type of emission that this accompanies other nuclear decay reactions, right? So when you have alpha decay, there's going to also be some gamma radiation that's emitted. Okay, so But there's typically a bit of the reason why it gets its own special category is, first of all, because it's a special type of radiation that's being emitted, a special photon that's being emitted, not a particle like our alpha particle or our beta particle. The other thing about it is that it usually occurs also with a little bit of a delay, right? So for example, if we had rhodium 103, rhodium is element 45, and it undergoes alpha decay. Okay, so first of all, based on what we've learned, you should be able to tell me what the products of that alpha decay reaction are. So everybody take a minute and tell me what those two products would be. All right, so the first alpha decay product is always that alpha particle, helium-4. Right, so then I just have to do my conservation of matter. So the other thing is going to be TC, or technetium. Technetium is 43. Okay. But it turns out that this technetium produced, so first of all, the mass number would be 99. And then we put a little M afterwards. This M means that it is metastable. Meaning it will undergo, not beta, sorry, gamma emission. Right, so first is the alpha decay. Gamma ray emission accompanies these other types of emission, but what we get is this unstable or metastable nuclei of technetium, which will then further undergo a gamma emission. So a gamma particle, because it is a photon, it doesn't have any protons associated with it. It also doesn't have any mass. Photons are kind of weird like that. All right, and so what I get out of that is the same exact mass number and same exact number of protons, just now the more stable nuclei. So it doesn't have that M indicating it's unstable or would undergo gamma ray emission. Okay, and again, this little gamma here, this is what we call our gamma particle, which is a photon. All right. Let's condense some stuff here. All right, so actually before we go, there are two more categories, but before we go on comparing alpha, beta, and gamma, there's sort of two considerations with regard to these types of nuclear reactions, and this is the ionizing power of that particle that's emitted, either the alpha particle, the beta particle, or that gamma particle, that gamma photon. Ionizing power is more or less the energy released. So how high energy that particle is. And here, the more massive particle, which is that alpha particle, right? That's quite huge compared to a beta particle, which is an electron that has some mass, but not really much. And then a gamma particle, which is this massless photon. So an alpha particle has greater ionizing power than a beta particle, has greater ionizing power than a gamma particle, right? Just the energy that's released when that particle flies away. All right. But the other thing that's considered is the penetrating power of that particle released, right? And this is sort of exactly what the name implies, just the ability to penetrate different materials. And here it's the exact opposite consideration, right? That photon with its lack of mass has a much greater penetrating power than an electron, much greater than an alpha particle, because alpha particles are just so massive. All right, so then our last two categories here are what's called positron emission. All right, positron emission is kind of the opposite of what we saw for beta decay. It's now a proton becoming a neutron and what's called a positron. And this is a new type of particle that you've never heard of before. Okay, so we have, so this is kind of like bizarre high energy physics here, but for every particle, for every type of particle that exists, okay, and this is actually true for every type of particle that you can think of, we have, so for example, an electron. There exists what's called an antiparticle. And in that case, that would be a positron. Right, so our particle is the electron. Our antiparticle is what's called the positron. This is a particle that has essentially all the same features as an electron. It's got the spin, it's got the same mass, but unlike an electron, which has a negative charge, positrons have a positive charge. All right, and this is just some like, to be honest, I'm not a high energy physicist, but this is some underlying theory of how matter works, how our universe works, that for every type of particle, there's like this equal and opposite antiparticle that also exists. What's more is that if you take your particle and your antiparticle and you combine them together, so if we take an electron, in nuclear chemistry, electrons are represented with 0 mass and a -1 charge, 0 mass number. And our positron is the same thing, but with a positive charge. So this is an electron. This is a positron. If you take a positron and an electron and you combine them together, they what's called annihilate one another. And you just get a release of energy, a release of photons. It's kind of like a bizarre thing. So we haven't really heard of positrons because they don't really exist in our universe for any long period of time because of this reaction right here. If you did have a positron, it would find an electron, they would annihilate one another. It's thought that at the beginning of the universe, there were pretty similar number of positrons and electrons, particles and antiparticles, but slightly more particles. And so eventually all the positrons found electrons, annihilated themselves, and what was left over is that small abundance of the electrons. All right. A little bit high energy physics, more in depth than we need to sort of go here. But yes, that's what an antiparticle is. So for positron emission, what would that look like? Is again, your proton is being converted into a neutron. So similar to what we saw for beta decay, our mass number doesn't change, right? Because protons plus neutrons stays the same. But again, our proton became a neutron. So our number of protons decreases by 1, right? And then we have that positron that's emitted. So if you look at this type of reaction stacked on top of your beta decay, you will see that it's very similar, except for instead of the number of protons going up, we have our number of protons goes down by 1. All right, and then the last one is what's called electron capture. Okay, this is where, unlike these other types of nuclear chemical reactions where you have proton, like things big being split up into smaller things, you have these decay sort of reactions. This is actually a reaction where an electron is absorbed. So we have a proton combining with an electron to produce a neutron. Okay. The net effect is very similar to what we see in our positron emission, meaning that we start out with something so like ruthenium. It's going to combine with an electron. But now, right, a proton got converted into a neutron, so the mass number stays the same. But now it's going to decrease because a proton got converted into a neutron. My number of protons decreases. Right, so again, number of protons goes down by 1. So same net effect as the what we saw for the positron emission. All right.
So for the positron, you put the number of protons goes down by 1. Would it be going up by 1 then, since it turns from 14 to 15?
No, it's turning from 15 to 14.
Oh, okay, because you're going in the room. Okay, I get it now.
Yeah.
Thank you.
Yeah, no worries. So in both of these, you have the same net effect of a proton being converted to a neutron, which is why the mass number stays the same, but the atomic number goes down. All right. So then looking at this here, how can we sort of figure out what a particular isotope would undergo? Right. So for example, if we have something, so here's our, let's say our ruthenium 100 is apparently stable. Well, what if I pick something all the way up here, like ruthenium, I don't even know, 44 plus 70, yeah, 114 or something like that, where it's got too many neutrons? What is that going to undergo, right? So if we look at this ratio of neutrons to protons, if it's too high, well, then it wants to get rid of those neutrons, or rather it's going to convert those neutrons into protons to help bring it down, or sort of over this way here. I guess it would actually go down and over, right? And that process would be that beta decay, right? So if that nuclei is too large to be stable, it's going to want to undergo beta decay because that converts neutrons into protons. Well, what if I do the opposite side and I pick one down here where my N over Z is too low? Okay, well, then it's going to want to do the opposite. It's going to want to undergo these processes in which protons are converted into neutrons, which would move it back this direction here. And so we had two different forms for that. That would be positron emission or electron capture. All right. And then what about that magical cutoff right here? That 83 mark? What if we have a particle that's got an atomic number greater than 83? Well, then it's got too much of everything, right? It's got too many protons and too many neutrons. So this is when you will see alpha decay as well as beta decay. So both of these kind of happening in tandem. Alpha decay is when a nuclei loses the most mass, right? We break off a helium atom. So sort of like we'll bring you down this way, right? If we started up here, our alpha decay would sort of take us down here, and we could make our way towards one of these more stable ones. Many of them would happen in multiple steps, but yes, so that's sort of how we can predict based on what our element is, what type of nuclear reaction it will undergo, right? So if you have too many neutrons, you're going to want to undergo beta decay. If you have too many protons, you're going to want to undergo either positron emission or electron capture. And if that nuclide is just too big, it's going to want to undergo alpha decay to make it much smaller, as well as this is usually accompanied by beta decay as well. All right, so that is our crash course into nuclear chemistry.